Hello everyone, welcome. This educational channel expounds topics in mathematics, civil engineering, and professional education subjects. This channel aims to simplify the lessons, and I am its founder, Bert, a Filipino licensed teacher and engineer. Thank you for watching.
Hello everyone, I will discuss the integrating factors found by inspection. This topic will be discussed in two videos and this is the first video. As shown in the list, our topic is the fifth lesson in the solution of some first-order differential equation. To understand our lesson, you should have a good background on lesson 1 to lesson 4, specifically from separation of variables to the linear equations of order 1. If you did not yet study these topics, you may spend time watching our videos on these topics. In our previous lesson, that is, linear differential equation of order 1, we converted this equation into an exact differential equations. We able to convert this by multiplying the equation by an integrating factor. However, there are many equations that already contain the common integrating factors. And these are the four common. First, we have dy over dx. Second, that is derivative of x over y. The third is derivative of y over x. And the fourth is the derivative of r times y over x. For example, here we have x dy plus y dx is equal to 4x dx. You notice if you are going to solve this problem, there is already an exact expression. So, you can immediately solve this given differential equation. The integral for this is equivalent to xy, which is this one, and the integral of 4x dx, that is 2x squared, then plus c. So this is the answer. And we have also other common exact differential equations. So for our lesson today, we are going to talk these integrating factors found by inspection. Specifically, our learning outcomes, at the end of the lesson, the students will be able to identify the common exact differential in differential equations and solve the differential equations containing the common integrating factors. Let us take the first common integrating factor. Differential of xy is equal to x dy plus y dx. Example 1. Solve the equation x dy plus y dx is equal to 3xy squared dy. As can be seen, this is an exact and the value for that is differential of xy. And then, I'm going to copy the right side, 3x y squared dy. As can be seen, the right side is not ready for integration. In particular, this is dy, but we have x variable. To eliminate our x variable here, we are going to multiply this equation by the integrating factor xy, and that is raised to a certain exponent. The exponent should be negative 1 in this case, such that x raised to negative 1 times x raised to 1, it should be 0. In other words, our n here should be a value such that the variable to be eliminated here should be able to eliminate. And the product here is xy raised to negative 1. The differential of xy equals now to 3. X is cancelled, then y. 2 times negative 1 is 1. Then differential of y. Take note, this is y raised to 1 and that is not y prime. Now both sides are ready for integration. For the left side, we are going to use here the ln formula. So I'm going to write this as differential of xy over xy. Then in the right side, you have 3 integral of y dy. Integrate the left side, we have here ln of xy is equal to 3 y squared over 2 plus c. Then simplify ln of xy. This is 3 halves y squared plus c. This is our final answer. How about if the dy here is changed to dx? And that will be our next example. So we have here x dy plus y dx equals to 3x y squared, and by this time this is dx. Similar to the previous example, we are going to substitute the left side by the differential of xy. Then this is equal to 3x y squared dx. The right side cannot be integrated because of our y squared. We have to eliminate this one. We can do eliminating y squared by multiplying the whole equation by our integrating factor xy, and it should be raised to negative 2. So that y raised to negative 2 times y squared is cancelled. So we will now multiply the integrating factor to the whole equation. This is now x, y raised to negative 2, then differential of xy. That is equal to 3, then x times x raised to negative 2, that is x raised to negative 1. Y squared is cancelled, then we have here dx. Now our equation is ready for integration. In particular, the left side use power formula. Okay, so we are going to integrate now the left side. Using the power formula, that is xy, negative 2 plus 1 is negative 1 all over negative 1 equals, for the right side, use now natural logarithm. Actually, this is integral of dx over x, and that is ln of x, then plus c. And simplify the left side, this is negative 1 over xy equals 3 ln of x plus c. To simplify this, we are going to multiply this one by xy. So this is negative 1 is equal to, we have here 3 xy ln of x plus c xy. This can be our final answer. Our next example, solve the equation x dy plus y dx equals to y squared dy over x cubed. You notice our right terms contain of the variable x cubed, and this is the difference from the previous example. For the solution, similar to the previous, we are going to substitute this exact, that is differential of xy, that is equal to the y squared dy over x cubed. Now on the right side, we need to eliminate x cubed. To eliminate this x cubed, we are going to multiply again the whole equation by xy and raised to n. Our n here is equals to 3. Take note, our x cubed here for this denominator will be transposed to the numerator, so the exponent will become negative 3. And x raised to negative 3 times x cubed, that would be cancel. Or in short, if you have here the x cubed divide x cubed, then that is cancel. The result now for this, we have xy cubed, the differential of xy equals, as I have mentioned, x cubed is cancelled, then y squared times y cubed is y raised to 5 dy. Next, we are going to integrate. The answer for the left side is xy raised to 3 plus 1 is 4 over 4. This is using power formula. Use also power formula in the right side. That is y, 5 plus 1 is 6 over 6, then plus c. Then simplify, we're going to multiply this by 12. So 12 divided 4, you have here 3, then you have x4, y4 is equal to 12 divided 6 is 2, then y raised to 6 plus c. Constant times 12 is still constant. So this is now our final answer. As observed in our examples 1 and 2, one important step in finding the solution is the determination of the integrating factor. So let's practice determining it. Example 3. Determine the integrating factor of the following differential equations. The two equations here have the same terms in the left side. Specifically, the left side is y dx plus x dy, and the right side contains dy terms. However, in the first equation, the variable x is numerator while the variable y is denominator. Conversely, in the second equation, the variable x is denominator while the variable y is numerator. So, let's observe how to find the integrating factor of these two equations. For our letter A example, I'm going to substitute the value of this exact expression, that is differential of xy, and I'm going to copy the right terms, that is 5x squared dy over y cubed. As noticed, the right member is not ready for integration. It is because we have dy here, but we have also variable x. So we need to eliminate x. And because of that, we need to multiply this by the integrating factor xy raised to n. Take note, you don't need to multiply the equation by the integrating factor xy raised to n if there is no variable to be eliminated on the right side. Again, when the right side is ready for integration, you don't need to multiply the equation by xy. However, in this equation, there is a variable x that we have to eliminate. So we multiply the equation by xy raised to n. And the exponent n here should be equivalent to negative 2, such that our x here can be eliminated. Or else, you can also write xy in the denominator, and our exponent here is equivalent to 2. Take note, xy raised to negative 2 is just equivalent to 1 over xy raised to 2. So it's up to you which of these two is your preference. But in my side, I prefer the second. So I may use this in our example. So I will multiply this by 1 over xy raised to n. And our value for n here is equivalent to positive 2. So let's do the multiplication. We have here differential of xy over the xy raised to 2. On the right side, we have 5. Then x squared is already cancelled. And then we have now dy. Then y cubed times y squared is y raised to the 5th power. And now, you can already integrate our equation. But we are going to end in this line because our intention is only to determine the integrating factor. I hope in this line you can integrate this equation. But to give you a hint, the left side you are going to use power formula as well as the right side. Then let's move to letter B example. As noticed in our letter B example, our x here on the right side is now written here in the denominator. And our variable y from the denominator in example A, that is now numerator in example B. So what's the difference? Again, I'm going to substitute the value for this exact differential, which is dxy. And that is now equivalent to 5y cubed dy over x squared. Then I'm going to multiply this by xy raised to n. We're going to eliminate x, and the value for n here should be equivalent to positive 2. So with this, our variable x in denominator can be eliminated. And now I will do the multiplication. We have here xy square, then differential of xy is equal to 5y cubed dy. And then in this line, you can proceed integrating the equation. Again, you are going to use power formula in both sides of the equation. In our example A and B, how about when this dy is changed to dx? And that is now our example C and D. The difference between A and C is only this letter. So from dy, that is changed to dx. And also between B and D, from dy, that is changed to dx. Nevertheless, the process is just the same. Similar to letter A, in our solution, we are going to substitute the equivalent of this exact expression, that is differential of xy, and that is equivalent to 5x squared dx all over y cubed. By this time, we are going to eliminate y. So, our exponent for the integrating factor xy, it should be 3. So that this variable y cubed will be cancelled. So we have here xy cubed differential of xy is equal to 5 is equal to 5x, that is x squared times x cubed is x raised to the 5th power dx. So comparing our example A and C, our exponent n here is the exponent of x. But in letter C, our exponent n here is the exponent of y. And this variable x or y are the variables to be eliminated. For letter D, we are going to substitute again the differential of xy. And that is equivalent to 5y cubed dx over x squared. In this equation, we need to eliminate y cubed in the numerator. So if we are going to multiply this, as I have mentioned, I prepare to write xy in the denominator. And I'm going to copy the exponent 3. So simplifying this, we have differential of xy over xy raised to 3 is equal to, our y is already cancelled, so we have here 5 dx, then x raised to the 5th power. I hope in this, for example, you already have an idea when to multiply the equation by an integrating factor. As I have mentioned, you need to multiply it by xy if the right side is not ready for integration. And also, you already know what should be the value of n if you will multiply the equation by the integrating factor. We are going to proceed to the second common integrating factor. That is the quotient formula. Specifically, the differential of x over y is equal to y dx minus x dy over y squared. You will use this integrating factor if you found this numerator in the equation. That is y dx minus x dy. Usually, the typical equation is y dx minus x dy, and on the right side is the function of xy dx, or it can be dy. Y dx minus x dy, then you have the function of xy dy. Let us now apply this integrating factor to our example 4. Solve the equation y dx minus x dy is equal to 2x squared y squared dx. You notice the left side is now y dx minus x dy. So that is the numerator to our common integrating factor. Therefore, we can solve this problem using this common integrating factor. We are going to rewrite the left members into this rational expression. So we are going to divide the whole equation by 2. I'm going to rewrite the given equation and then divide both sides by y squared. I divided 1 by y squared because we are going to follow this format here. And the right side should also be divided by y squared. The left side is now equivalent to the differential of x over y. Then on the right side, we have here 2x squared dx. As noticed, the right side is ready for integration. That means we are going to proceed integrating the equation. So that is integral of the differential of xy is equal to 2, the constant, and integrating of x squared dx. Then, integral and derivative cancel. We have here x over y and is equal to 2. Then we have here, use the product formula, that is x cubed over 3 plus the constant. Then simplify, x over y is equal to 2x cubed over 3 plus c, and this is our answer. Then the question, how about if this right side is not ready for integration? So that would be our next example. Hello everyone, this is the end of our first video on the integrating factors found by inspection. For the continuation, you may proceed to the second video on this topic.